Welcome back to Module 204E Part 2, where we're going to look at Objectives 4 through 7. In Objective number 4, we're going to look at the different reasons why we need to have overload devices for our motors and what they really do. Remember that our overcurrent devices are designed to protect our wires, and they are there in case of a short circuit incident where we're going to have an extremely high current. But if we only have a slightly high current, that current could still be damaging because it's going to create excessive heat. The primary purpose of an overload device is to prevent that overheating. So this will handle short durations of an overload condition, but if the motor is overloading for too long, it is going to open to protect the motor windings. The motor nameplate values will specify the temperature rise value that the motor can safely operate at, and that is the value above the ambient air temperature the motor can safely operate at continuously. The things that we need to consider in regards to what could cause an unsafe temperature rise are the magnitude of the load current, the duration of the overload condition, how often the motor is going to start, so the motor start frequency, the time duration it takes to get the motor from a starting position to a full speed condition, any ambient temperatures that might be affecting my overloads, my motor's cooling ability, as well as the motor's duty cycle. All these different things will create heat or affect the heat values in their own way. Whenever we are working with three-phase motors, we have to be aware that there are certain conditions that could cause unnecessary heating as well as excessive loading on our motors. The primary condition that we are going to be concerned with is what is called single phasing. Before we can understand what single phasing is, first we need to understand how a three-phase motor works. A three-phase motor works on the principle that we're going to have a rotating magnetic field based on the sine wave of the three different phases that we're going to be putting into this. So I have line 1, line 2, and line 3, and all three of those phases are 120 electrical degrees from each other. When I apply that to a motor, I'm going to have different windings that are going to be placed at 120 degrees physically from each other, and each one of those will be associated with a different phase. How this works is that now I'm going to have a rotating magnetic field where the maximum strength between any of those 2 points is going to be rotating around in either clockwise or counterclockwise direction. Since a three-phase motor requires all three phases in order to create a rotating magnetic field, single phasing is when we only have 2 of those 3 phases actually operating. And in this case, we basically have one phase working since I have a single voltage between 2 lines. This can affect our motors in a number of different ways. First of all, it will cause a very high current in the remaining 2 phases. The current will actually go up by 173% on each one of those 2 remaining lines. This can also cause severe damage due to excessive heat. What we will also find in the conditioning of single phasing is that if the motor has a blown fuse, which would create a single phase condition, then the motor itself will not start and it will simply sit there and hum instead. I posted a video in Blackboard on single phasing from BTC Instrumentation. Make sure you watch that video. It gives you a really good demonstration of what is happening within a single phase environment. There are multiple different conditions that could cause single phasing of a motor, including a loose wiring connection or broken conductor or winding. The more likely ones are that we have a blown fuse on one of my phases, or I have a burnt out power contact. Another thing that could happen inside my contactor, but is somewhat rare, is I could have one burnt out overload heater where the other 2 are still fine. Any of these conditions could cause single phasing, and we need to be able to recognize not only what single phasing is, but how to identify which of these conditions is causing the problem. We're now going to dive back into code and look at the requirements that we have for my overload devices. The section of code that deals with overload devices starts at 28300, and we're going to look at a few of these rules, starting with 28304 subrule 1b. We can use fuses as overload devices, but that's not very common. Normally we use overload heaters. Therefore, the code says that if we're going to use devices other than fuses, we're going to look at table 25. Table 25 is going to tell us how many overload devices do we need to have inside our starter, and typically it's going to be 1 per ungrounded conductor. Rule 28306 refers to the service factor on the motor nameplate. In order to properly set or properly size our overload heaters, we need to pay attention to the service factor rating of the motor. The service factor is the ability of the motor to work at longer durations at a higher overload condition, and it could range anywhere from not being rated at all up to 1.5. Rule 28306 states that the overload is to be rated at 125% of the full load and capacity if the service factor is 1.15 or greater. So we have to look at the service factor. If our service factor is rated to work at 115%, then we are allowed to size our overloads slightly higher at 125% of what my full load current rating is going to be. If my service factor is less than 1.15 or it is unmarked, the most I can set my overloads at is 115%. Some overloads are adjustable, and I can set the trip setting to wherever it is going to be most practical for my motor. However, on ones that have overload heaters, I would need to select the appropriate heater size in order to match the service factor. The last thing we're going to look at is the different types of overload devices I can use for my overload protection. The job of the thermal overload is to sense the current in the motor circuit and then respond to the overload condition. They are rated by a trip class, which is how fast they respond to the overcurrent, and they're classed in either 10s, 20s, or 30s. Thermal overloads detect the amount of heat that is produced by the overload heaters. The heaters will then melt the alloy, which is a solder pot underneath them, and then the spring-loaded wheel will turn and opens up the normally closed contacts and interrupts the control circuit. Once the solder has a chance to cool and reharden, then the system is resettable. This reacts very well to single phasing, however it is affected by the ambient temperature changes around it. A warmer room, for example, could allow this to trip prematurely early. With the bimetallic strip type overload, we have a heater that is wound around a bimetal strip. The heaters will warm the bimetal strip and then that will open up the contacts. The contacts will auto-reset when they cool back down again. This type of overload can compensate for ambient temperatures, and the individual heaters are selected according to their full load and capacity. They are non-individual units and they have an adjustment dial. The last type of overload we have is the magnetic flux overloads. These rely on the magnetic flux that are created by the motor current. These are strictly current sensitive and they are not at all affected by the ambient temperature around them. And there's two different design types. First, we could have a coil connected in series with the motor, and that operates an armature to open up the contacts. And secondly, we could have a current transformer placed around the motor conductor which will energize a separate relay. These are considered to be an instantaneous trip device and they can be adjusted for our trip value. These devices can be overly sensitive during startup due to the inrush current, so they must either be bypassed or they must include a dashpot to delay their function. Electronic overload relays typically use current transformers and are adjustable and programmable. We normally see this in more critical operations, and they are more efficient because they don't create any heat. Normally, whenever we use a magnetic flux overload, it will be incorporated into a PLC, and they are often used with variable frequency drive units in order to limit that initial inrush current. You've now reached the end of Module 204E. Make sure you are reviewing both the videos as well as your module, and then return to Blackboard. Do a review for Modules 204A through E, and then you can complete the review for test S4-1.